There it goes. There's still a lot of strength left.
Today, we're diving into polysulfone, specifically Thermax PSU filament from 3DX Tech, available at fissionminer.com/materials, because that's right, we are a business and we're here to help you use this stuff and everything else we sell on our site. But this is a high-performance thermoplastic that's been used in hospitals, filtration systems, fighter jets, even outer space. Literally. So in this video, we're going to break down exactly what it is, where it's used, how it prints, and why it might be the material you've been overlooking for your high temperature builds. So what is PSU? Polysulfone. It's a high-performance amorphous thermoplastic that's been around since around the 1960s, and originally it was commercialized by Union Carbide under the name of UDEL. Now it's part of the sulfone polymer family, known for heat resistance, toughness, dimensional stability, and exceptional performance in wet or sterilizing environments. So unlike some other semi-crystalline polymers, PSU has 0 crystalline regions, which gives it excellent dimensional stability and the transparency that it's known for, but it also does make it a little more sensitive to stress cracking when exposed to certain solvents, and we've actually seen this with our filament and mineral oils and whatnot. Now, chemically, it's built on a backbone of aromatic rings, ether linkages, and sulfonyl group. That sulfonyl piece is absolutely key. It gives PSU its high thermal stability, as well as its resistance to oxidation and even some radiation resistance. Now, here's a fun fact. PSU was actually used in NASA's Apollo program. The outer visor on the space helmets worn by the astronauts during the moon landings was made from polysulfone. But why? Several reasons. Number one, it resists UV radiation and ionizing radiation better than most clear plastics. It handles thermal extremes without warping, and it's optically transparent with excellent impact resistance. It also doesn't outgas, which is kind of a big deal in a vacuum environment. So some grades are actually UL94 V0 rated for flame, smoke, and toxicity, so that's also a plus. So where is PSU used? Let's check out the industries, and more importantly, who is actually using it. So in medical and healthcare, we've got Fresenius Medical, Baxter, Nipro. They all use PSU in dialysis membranes and blood filters, much thanks to its biocompatibility and its ability to withstand hundreds of sterilization cycles, and that's both heat and chemical. GE Healthcare and Medtronic use it in surgical instruments, sterilization trays, and fluid connectors. Nalgene actually makes lab-grade sample containers and bottles out of PSU, and it's tough, it's chemically resistant, and it can survive repeated autoclaving. In filtration and water systems, you've got 3M, Pall Corporation, and Evoqua. They all use PSU in ultrafiltration membranes, especially in biotech, food processing, and even the municipal water treatment plants. It's the backbone of many reverse osmosis membranes due to the stability in hot, chemically active water. I've got one of these in the office and my house. So if you've got a reverse osmosis system, you've got PSU. In the food and beverage category, we've got Bunn and even Keurig, which I'm sure most of you know. They've all used PSU in the hot water tanks, the coffee dispensers, and all the microwave-safe parts. So one of our early customers here at Vision Miner was actually making competition pour-overs. Pour-over is a thing that you put coffee in and you just slow drip the water over it and it goes through. And so he designed it in such a way that it would get really good extraction. They did that whole thing, but he also made these steam filters for these really expensive Italian coffee machines. We actually have one of his parts right here. For Litmus Coffee Labs, this is one of those things where it would replace the part that distributes the water over the coffee. And so it's, super high temp resistance and food grade and all that stuff. And this was done with a 0.8 nozzle, I believe. So it's 2 walls around and 2 layers on the bottom. They made a ton of these back in the day and worked out really well for them. We also have milking machines and food service trays, and they use PSU for hot or acidic or even detergent heavy environments. It's also approved by the FDA for NSF food contact, making it a go-to in professional kitchens and food plants. In the automotive category, we've got Delphi, Bosch, and Vallejo using it for sensor housings, fuel line components, electrical insulators, and under the hood, where temperatures and vibration will kill all other plastics. Now, PSU is often chosen over polycarbonate or nylon when chemical resistance and dimensional stability are critical. In aerospace, it's used in aircraft interior panels, ducting, light covers, anywhere where low smoke, low toxicity, and flame resistance are critical. It's used by companies like Siemens and ABB for high-temperature electrical insulators, coils, switch housings, connectors. PSU holds up great even after long exposure to heat, humidity, and other high-voltage stresses. And its electrical properties are very consistent in these environments. And of course, the military, they've used it for years. PSU has been found in field-grade fluid fittings, protective housings, even equipment that sees combat conditions. Its impact resistance and its low flammability are critical in mission-critical environments. All right, so let's get into some technical details straight from the TDS. The tensile strength is about 70 megapascals. The tensile modulus, 2.5 to 2.7 gigapascals. The flexural strength is 105 to 106 megapascals. Flexural modulus of 2.6 to 2.76 gigapascals, with a glass transition temperature of 187 to 190 Celsius and an HDT at 1.8 megapascals of about 175 Celsius, giving it a max continuous use temperature of about 160 Celsius. It's also got that UL94 V0 rating, depending on the thickness, and water absorption of about 0.2 to 0.3%, with a dielectric strength of 16.7 to 17 kilovolts per millimeter. So what makes PSU special, or why does PSU really stand out? One of the big things is that it doesn't degrade in steam or water and moisture, which means it's perfect for autoclaves and hot fluid systems like this coffee machine. It also doesn't warp under load, even at high temperatures and humidities. It's inherently flame resistant with low smoke profile, so it doesn't smoke out an entire building if you catch it on fire. It's also really chemically tough, standing up to acids, bases, oils. It's also clear, so you can create strong, translucent parts straight off the printer. Now, it's really rare to actually find a polymer that's transparent, strong, heat stable, sterilizable, but that's what we got when we're looking at PSU. Now on the 22 IDEX, our printer here at VisionMiner that we manufacture, right behind me, you'll see it there. How does this stuff print? We've been running it for many years and it prints very clean. In general though, you can get a really good surface finish with smooth walls, really good interlayer adhesion and bonding, and surprisingly forgiving print behavior for a high temp polymer. We printed all sorts of stuff like pump housings, sterilization trays, sensor covers, little jigs and fixtures like this, even custom manifolds for food and medical setups, much of which we can't actually show because our print service is shrouded in NDAs. That's why we always look to you guys. If you have something where this is really applicable, send us your part. We might actually print it and do a feature on it and do a video. Let us know. It's not super brittle. It doesn't ooze too much when you're printing, and it performs just like injection molded PSU as long as you prep it right. Prep is always important. But first, what do you need to even print PSU? Well, your nozzle needs to go to at least 360 to 370 or so Celsius. The bed temperature, 140 to 160, sometimes higher. The chamber temperature, at least 90 Celsius. The higher the better. If you can print this at 140, 160, great. Layer height, anywhere from 0.1 to 0.2 is solid. Nozzle, you can print it easily out of a 0.2 millimeter nozzle. We've even done a lot of parts on a 0.1 nozzle, which was actually a custom product that we made. Got some really phenomenal results with it. The most important part, especially in the high temperature filaments, you must dry this filament. At least 3 to 4 hours between 130 to 160 Celsius to really get it dry. That is absolutely completely critical. Now ideally you can just leave it in a vacuum oven overnight at about 120 to 140 Celsius and you'll be totally fine. If you don't, PSU is very hygroscopic, so if you skip drying it, you're going to get steam bubbles, rough surfaces, and just generally ugly, weak prints. So we recommend using either our vacuum oven, available at visionminer.com, or grab one of our drying kits over at visionminer/drykit. With the vacuum pump and everything, it will make your life much easier. That's the story, that's the data. Thermax PSU, a polymer that's been to the moon, survived medical sterilizers, filtered the world's clean water, and still prints beautifully on our 22 IDEX, which you can find at visionminer.com/22 IDEX. But now we're gonna pass this along to Cole and throw some parts into testing, twisting, breaking, burning, and more. So let's see how this material actually performs in the real world.
Hello, ladies and gentlemen, and welcome back to the testing portion of this PSU video. My name's Cole with VisionMiner, and I'm going to be putting this material through its paces so that you actually have a representation, a visual representation of what these materials are capable of. So the way we do this is I will hold a propane torch on its highest setting 1 inch away from this material for a duration of 5 seconds. And then we're going to analyze exactly how the material behaved afterwards, during, and how long it takes for it to actually stop smoking. So self-extinguish. And there's no other way to get these values than to do it. So I'm actually going to use my phone here as a stopwatch so I make sure we get accurate times. For the sake of consistency, right there. All right. And time begins now. .37, so 5 seconds again at a distance of 1 inch with a propane torch on its highest setting, and we got it. I'm going to see how long it takes to actually stop smoking. .57 seconds, so around 5 seconds, 4.5 seconds for it to stop smoking. Now, if I were to do this with a piece of PLA, this would actually continue to burn like a candle all the way down while letting off terribly noxious fumes. So polysulfone, sulfonates. What does that mean? Well, it means that this is far more hydrophobic than it would be without that group. It also does not melt cleanly, as you can see here. It does off-gas kind of a sooty smoke, but it's for such a short period of time that, I mean, it's actually a benefit that it's self-extinguishing. So one thing that's interesting about this material is that it doesn't particularly melt cleanly. You're seeing it decompose, and that's where we're getting this residue. But below that residue, there's still a ton of material. And if we actually hit it again, it's already, there we go. It takes a lot more pressure, but it's about to be solidified again. And that was exposed to 3,600 degrees Fahrenheit for 5 seconds for a second, maybe third time. Already almost usable again. What's below this? How much material did we lose? We have charring, barely any loss of material. And just for fun, let's do one more where I get some high-speed footage for you, some slow-mo, so you can see what's actually going on when I burn it. All right, here we go. And so my favorite part of this whole process is always looking under the microscope because you get to see every little facet of the print. You can also figure out exactly how it failed, where it failed, if it's a clean break and so on, or if it's, directly on a layer line to know if we need to change temperature, speeds, extrusion multiplier. And there are just so many things that you would never be able to see with the naked eye until you look at it under one of these microscopes. Now, this is not a fancy microscope. I think you can get this on Amazon for, a few $100. And there are definitely cheaper ones that do the same job. Nothing fancy, but if you just want to get a closer look at your work, I can't recommend these enough. It's actually really entertaining. And if you get some data from it, it's a win-win for everybody. I often use the microscope to actually check how my retractions are doing, if I need to change the distance, speed, so on and so forth, if I coast wipe, you name it. You can pretty much debug, you can pretty much get to the bottom of most printing issues by just really looking at it closely. Now, of course, that's going into extreme detail, but that's kind of what we do here. And sometimes things are just really pretty. So, self-extinguishing, very excellent temperature resistance. And because it is a sulfone, it is far less likely to absorb water and is overall just a more durable material. Let's put this thing into a testing machine and get some actual values. We have 2 sample bars here. One is printed on the XY, the other is printed on the Z, so we can get a sense of strength for both. and give you an actual number and figure. So let's start breaking some parts. Over to the universal testing machine. By the way, that's just a machine that basically pulls, pushes, bends materials until they break. And that way we can see how strong they really are. This is our first example of XY orientation, and as you can see, it reaches over 2,000, actually 2,072, which is 465.9 pounds. Now let's transition over to the Z-axis samples. Now the Z-axis samples are just printed straight up and down on the build plate so that the layer lines are actually parallel with the build plate. Very tricky to print and always weaker. The weak point is always going to be the Z-axis where the layers interface with each other, basically on FDM prints. And this first print gets to 996 newtons. Torsion test. Let's begin. 9.9. Write that down. In this portion of the video called the bend and break test, you're going to see us bending it and then trying to break it. So here's the bending portion, and it bent until it broke. And now the break test, and we're going to hit it until it breaks. And there's the break. I also just want to speak about my personal thoughts. Rob gave you all the data on PSU, but let me tell you, as someone who's used it a lot, it's a high temp material. So yes, it's a bit difficult to print and figure out, but it's extremely forgiving. Compared to PEEK, this thing is the difference between, it's like the difference between ABS and PLA. This stuff behaves really well. It looks beautiful. The finish is beautiful. It prints very well as well. There's not a huge amount of tuning that needs to be done. If you get it from a reputable source like 3DX Tech, who I cannot recommend enough, the quality of their materials is every time is flawless. This is a wonderful material to work with. And if you're going to start working with it, understand that you're going to run into challenges that you have not faced before in any lower temp material. And we call lower temp materials, I'd say 320 degrees and below on the nozzle. This is a wonderful material just to use in place of PEEK. The chemical resistance, as Rob said, is awesome. Pick up a roll, try it out. This stuff is incredibly impressive. And if you are in a field like aerospace or something where you need UL 94V0 or any kind of UL rating, look at this material before you look at the bigger, more expensive materials. It's going to make your life easier and it's going to perform just as well. And it's going to look better. This is so pretty. We're putting together a spreadsheet so that as these videos progress, you'll be able to go and check this sheet against, PLA, ABS, PETG will be our baseline, how these different materials stack up and behave. We're still figuring out this whole testing process, and we actually have way more that we're going to be doing. We are going to be using high pressure air, and I mean thousands of PSI, in pressure vessels to test what these things can withstand. We're going to be testing water ingress. And if you can make the part, what's the dang word? Porosity, that's right. And porosity, chemicals, extremely caustic chemicals over long periods of time, what happens, degradation. So please know that this is the very infancy of this whole project. And it would be cool if you subscribe now, because I promise you that these tests in a few months are going to be overkill. Huge. I'm talking custom Lexan polycarbonate blast chambers, which we've shattered already in early testing. Thank you guys for watching. Thank you for having fun with me and messing around. It's going to get a lot more scientific and a lot more fun. So please subscribe, and I'll see you in the next video. Wait. If you have ideas for testing, legitimately, like I'm open to any kinds of useful types of testing that I haven't thought of that'll actually give us data. Let me know down in the comments. Let me know what you would like to see that you haven't seen other people do. We'll do it. We'll do it. So I try to give you the most unbiased, fair opinion of this stuff as I can by testing it and sharing my experience using it. I'm Cole with Vision Miner. Stick around for the next one.